Welcome to MOVI-C Control Cabinet Products Basic to Intermediate Training. This is session 18, and this happens to be the second to last session, so we are almost finished with this class. As you can see, this again is a pause from labs. We're going to spend some time learning about a topic that is very important to the next lab and to more advanced topics that you may choose to study after this course. That topic is referencing. Referencing is something that must always be done before you can do any kind of positioning operation, so it's very important to understand it and how it works. So we're going to spend some time going through some of the nuances of referencing. Let's get started. First of all, a few important points. By default, MOVI-C products use revolutions or revs as positioning units. This is different from some earlier SEW products. But if you think about it, it makes some sense. After all, motors produce rotary motion, so of course that rotary motion ultimately, regardless of how it positions, is really what's driving things. So understanding how many revolutions or fractions of a revolution you've turned does have a certain logic to it. In general, positions are specified in 1/100th of a revolution with 2 pseudo-decimal places. Now, what do I mean by that? Simply this: you don't actually enter a real decimal place. You do something like this. If you enter the number 83,729, that actually equals 837.29 revolutions. So there's actually an imaginary decimal point in there, and you just have to sort of visualize it. Be aware it is possible to create user-defined units. You aren't stuck with revolutions. That's simply the default. We will probably release a short training on how to set up user-defined units on our YouTube channel in the future, so keep an eye out for that. Now, throughout this course, we've been reminding you that you need to have an encoder to support certain motor control modes, but now we're going to dig a little deeper into encoders and the way they work and what you can learn from them. Encoders divide broadly into 2 categories. There are incremental encoders and absolute encoders. Incremental encoders are more common because they're less expensive. An incremental encoder's main purpose is to report the motor's speed, but it can be used for positioning as well, although with a certain limitation, which we'll discuss as we go along. Most incremental encoders provide information by using interrupter disks, and this is one that I took apart and took a photograph of the interrupter disk, and you can see it has lots of tiny little lines scored on it. It's actually designed to reflect light. There is a light source and a sensor that can read those little marks on the disk, and as they turn, they alternately reflect and interrupt the beam of light. And so those optical pulses generate electrical pulses, which are used for interpreting what's going on with the encoder. This is what most interrupter disks look like if you look more closely at them. They actually have several tracks around them with marks on them. It's not just one group of markings. There's the A track and the B track. The markings are identical, but they are offset from each other, as you can see. The reason they're set up that way is because you can determine the direction the disk is rotating if you have 2 tracks. If you have just 1 track, you can't. So most interrupter disks have 2, so it provides direction and speed. The way it provides speed information is very much the way a speedometer works. You simply count how many pulses occur per second, and from that you can figure out how fast the disk is turning, how many revolutions it's turning per minute. So interrupter disks are a very simple way of providing very good information about what the motor's up to. Many encoders also include a 3rd track with just a single mark on it. This is called the 0 pulse mark, and its purpose is just to indicate where the encoder itself is within its rotation. Not all incremental encoders have a 0 pulse track, which, by the way, it's also called an index track, but many of them do, and it's often used in referencing, so it's very important to be aware of what it is. The second kind of encoder is called the absolute encoder. It's much more expensive, and you can see it's much more complex. This is one I took apart and took some pictures of. Absolute encoders are very useful for positioning because they give an actual position for every rotary position of their shaft. Incremental encoders just output pulses. Absolute encoders give numbers indicating where they are in the 0 to 360 degree rotation. They come in two forms. The less expensive version is the single turn, where the position repeats after one 360-degree rotation. Multi-turn are more sophisticated. They not only provide a single turn position, but they also keep track of the number of turns the encoder has made. Many of them, for example, can keep track of up to 4,096 rotations before the numbers start to repeat. The more money you pay, the more turns you can get. So absolute encoders have a lot of advantages. This is what an absolute encoder's disk looks like. They too use interrupter disks, but you can see they're a lot more complex. The absolute position tracks are actually binary numbers encoded on the disk, and as they turn, a series of sensors can pick out the light and dark patches and turn those into numbers. The outer section of the track is a regular incremental track, which can be used for speed determination, and the zero pulse mark may or may not be present there as well. So absolute encoders can do everything an incremental encoder can do usually, but they're definitely more costly, so many applications don't include them. Finally, I'd like to mention a third way that you can determine position. Now, this device is technically not an encoder, but we usually classify it with encoders because it effectively does the same thing, and that is the resolver. Resolvers are inexpensive alternatives to absolute encoders. They come on some servo motors. Now, how does a resolver differ from an encoder? Well, the big thing is it's an analog device, not a digital device. It's basically almost like the two halves of a transformer. Part of it is fixed and part of it is attached to the motor shaft. They're energized by a high-frequency alternating current, and they output an analog signal corresponding to the rotational position. You can see what it looks like there on the right. It's kind of a sine-cosine combination. The VFD has to read this analog signal, and it has to do some math on it, but from doing that, it can infer the rotational position. You can think of a resolver as effectively a kind of medium-grade single-turn absolute encoder in its performance. It is different, but you really don't have to worry about it because MOVI-C supports resolvers, and you're going to get a position back from it just like you would from a single-turn absolute encoder. So that's pretty much all you need to know about them at this point. Now we come back to referencing. What is referencing? Referencing is also called homing or zeroing, and what it does, it establishes the location of the machine zero position, which in SEW Eurodrive literature is often abbreviated MZP. This is the zero location from which all positions are referenced. All positioning applications must be referenced at least once before they can be operated. You have to find zero. Now, if you have an incremental encoder, this is the disadvantage of incremental encoders. They don't store the actual position. So every time you turn the application on, you've got to re-reference the encoder. You've got to go through this zeroing process. On the other hand, absolute encoders always know where they are, whether they're turned on or off, and as soon as they're powered up, they're ready to go. The only time you reference them is when you install them or if you make some kind of mechanical change to the application machinery. That is one reason absolute encoders are so nice. You don't have to keep re-referencing them. But either kind of encoder can be used to provide a position. It's just with incremental encoders, it's a little more work. The routine that you use to find machine zero, in other words, the way you reference the drive, is called the referencing type. Most VFDs that do positioning have several ways of doing it. MOVI-C is no exception. It has many different referencing types available, and that is what we're going to be spending some time learning about because I want you to understand how they work. MOVI-C actually has 10 different types, believe it or not. Now, in addition to the encoder itself, most referencing modes require some additional sensors which can be used to help with the referencing process. We're going to talk about these right here. One type is called the limit switch. Now, you're probably already familiar with limit switches. They're primarily safety devices meant to keep mechanical motion from going outside, usually two limits, right and left. They prevent the cart in this little application here from going off the track. So in their normal application, limit switches prevent movement outside of normal travel limits by tripping a fault condition on the inverter. They are, as you know from earlier labs we did, normally closed or active low sensors. However, they can also be used to detect position as well, because of course you know where they are, and if you tap the limit switch, you know where you are. So they are often used with the encoder to reference it. So for example, when you tap this limit switch here, you go from high to low, and then when you move off it, you go back high again. And when you go onto this one and tap it, you go from high to low, and then when you back off it, you go high again. So just by monitoring those signals, you can know where you are. If your encoder has a zero pulse, you can use it as a kind of application sensor because it will generate that pulse at a specific location on the encoder's shaft. In many referencing modes, you simply rotate till the next zero pulse comes, and then you are at a known mechanical position of the encoder. This may take up to almost a full revolution to reach the zero pulse mark if you've just gone past it. Zero pulses can be used by themselves or paired with another sensor. Typically, they're paired, usually not used by themselves, but it is possible, sort of like this. You rotate and move until you hit zero, and out comes the zero pulse, and you say, okay, I'm there, and maybe I'm referenced there. And then your third kind of application sensor is the reference cam. This is a contact sensor, and it's used to detect position. Usually the travel mechanism bumps the cam, and it outputs a pulse. They are normally open or active high sensors, so they're the opposite of limit switches, and that is because they are not mission critical. Usually non-mission critical things are active high because they're a little more intuitive, and also it prevents them from being falsely triggered if their power supply fails. So what you usually do with a reference cam is you simply move until you touch the cam, and then you back off it just until it clears, and then you're referenced. Cams can be used either alone or in a combination with limit switches or zero pulse signals. Let me show you how a cam sensor might work. Normally the cam is low, but as you approach it and tap it, it goes high. And then you know you're on the cam, and then you back away from it just until it goes low, and then you stop. So that's a very popular way to do referencing. You can also do a cam with a zero pulse. Let me show you how that works. It's the same general idea. You approach, tap, go high, back away, and then keep going just until the next zero pulse, and then stop. And at that point, you're referenced. That's just another way to do it. All right, we've gotten the hardware side of referencing out of the way. Now let's talk about the different referencing types and how they work, how they're different from each other. As I've said, MOVI-C supports 10 different types, but it's really not quite that formidable. There are really only 6 categories, and here they are. You can see many of them are actually pairs. The first type is zero pulse detection alone. You just look for a zero pulse. The second type involves a reference cam. There are 2 types here. The third type involves the limit switches. There are 2 types. There's another reference cam method, a pair of those. There's what's called no travel referencing, just one there, and then something called fixed stop referencing. Those are 2. Now you may wonder, why are there so many pairs? Well, there's no mystery about that. The paired types are identical except for the search direction. In other words, whether the motor turns clockwise or counterclockwise as it's seeking out the reference sensor. That's why there's so many pairs. I should also mention that some types optionally can include a zero pulse. In other words, they seek out the reference sensor and then they keep moving until the zero pulse occurs. Of course, this requires an encoder with a zero pulse. So if you add in the zero pulse option, there's probably really 16 types of referencing, but there's really only 6 main categories. What we're going to do is go through these. It won't actually take long, so don't think you're going to be here forever, but I think you do need to understand how the different reference types work. Before we can talk about those, though, I should mention that referencing takes place at 2 configurable speeds. You can set these speeds in the parameters, and there are 2 different ones. Now, why are there 2? Well, it's very simple. The first one is what's called the search speed. It tends to go fairly quickly as it seeks the sensor. And the second one, number 2, is the retraction speed. It's slower. You go very quickly to the sensor, and then you slow as you're tweaking your final position. Pretty simple. All right, let's go through the referencing types. This is type number 1. It uses just the 0 pulse on the encoder, so obviously you must have a 0 pulse equipped encoder. The goal is to be to the left of the first 0 pulse, in other words, counterclockwise. By the way, counterclockwise is considered left and clockwise right. So here's kind of how it works. You run counterclockwise or left at speed number 2. That's the slower speed, until the encoder outputs a 0 pulse. So this is what it looks like. You kind of creep until the 0 pulse arrives, and when it does, you say, good, I'm done, I stop, I'm referenced. Very simple. Here's 2 and 3. 2 and 3 are identical. They only differ in where you wind up with respect to the reference cam. One type you wind up on the left side, the other type you wind up on the right. Otherwise, pretty much the same thing. So let's look at just type 2. Type 3 is identical except where you wind up. So type 2, the goal is to be on the left side of the cam. So you move counterclockwise at the higher speed until you touch the cam, then you slow down and you keep moving counterclockwise just until you come off the cam, and then you say you're referenced. And this one does support the optional 0 pulse, so if you enable that, it will keep going just until the next 0 pulse occurs. If you were doing type 3, you would be on the other side of the cam when you're done, and you would have traveled in the other direction. All right, moving on. Type 4 and 5. The goal is to travel either to the right or the left limit switch. Very, very simple here. We'll look at type number 4, where you travel to the right limit switch. So you move at the higher speed until you tap the limit switch, and then you back away at the lower speed just until it releases. And this one requires the 0 pulse. It keeps moving until the next 0 pulse occurs, and then it declares itself referenced. Type number 5, it would be the same, except you'd be on the other limit switch. Type 7 or 8 is another type of reference cam mode. You notice the cam is not sorted in the middle like it was in the other reference cam type. It's close to the limit switch. So the idea is you put the cam near one of the limit switches and you travel and touch that cam. We're going to look at type number 8, where you travel to the cam located at the left limit switch. You move at the higher speed counterclockwise until you tap the cam. Then you back off at the lower speed until it releases, and optionally keep moving until the next 0 pulse if you've enabled that, and then you're referenced. Type 7 is the same, just the other limit switch. Type 9 is what I call the cheating type reference travel. This is the one we often use in classes because it's really easy to do. It's called no travel referencing. Basically, all you do is you manually move the device where you want it and then say, this is 0, be referenced. So the drive doesn't have to be enabled. There's no powered motion. If you're right at 0 when you start, you don't even have to touch it or move it. So when we do this in lab, of course, we just say, okay, we're referenced at the moment. We're 0 right here. And that works great in a class where you don't really have an application machine. But it's also useful in real-world applications when you install an absolute encoder or when you use some kind of manual referencing process. So here's kind of the idea. You manually move something around, get it where you want it to the machine 0, and then you trigger the mode and say, okay, we're referenced. Pretty nice. And then there's type 10 or 11. This one was not found in earlier SEW products, but it's a brand new kind of mode. In this one, you move until you contact a hard stop, either on the right or the left side. And what happens when you jam yourself against the stop, the torque suddenly rises because you can't move. The VFD detects that, realizes it's pushed against the stop, halts the drive, and says it's referenced. Kind of like this. We'll do type number 11, moving to the left. So we move at the slower speed until we're forced into the stop, the torque rises, and we say, okay, we're referenced. Pretty simple. Optionally, a limit switch or reference cam can be combined with this to detect your approach to the stop, but I didn't show that here. And there we go. We've just gotten through all the different types, so that actually was pretty painless. All right, now we move on to a topic that can actually be very confusing to some people, and I want to go through this carefully so you understand it. It's something called reference offsets. It's not something you must use, but it is very handy in certain situations. Let me explain. The distance between the referencing sensor, for example, in this case a cam, and the machine zero position is called the reference offset. Now maybe you're thinking, well, isn't the cam always at zero? And the answer is not necessarily. Many times it is, but sometimes it isn't. Sometimes the referencing sensor is at the actual machine zero position. So for example, this cam is in the middle of the travel range, and we've declared that to be the machine zero location. That's nice and simple, easy to understand, and if that is true, we say the reference offset is zero because there is no difference between the location of the sensor and the official zero position. So that's the easy one, and if that's the way your application works, then you just set the reference offset to zero in the parameters and forget about it. However, some applications are different. In those situations, maybe the sensor is not at zero. For example, notice here the cam is near the right limit switch, but the machine zero is in the middle of the travel range. Now, when this is true, the referencing sensor's position is not zero. And when you reference the drive, you're not actually sitting at zero, you're sitting at a different location. So we need the reference offset to tell us where zero actually is. So what we do is we measure the distance between the sensor and the actual machine zero position, and we set the reference offset accordingly. It tells you what the difference is between zero and the sensor. And by the way, that positive or negative sign matters because it says in which direction you're offset. So in this case, the offset could be, for example, positive 28,504 revolutions. Why positive? Because we are clockwise of the actual machine zero. When we're sitting on the cam, we've had to move clockwise to move away from machine zero, so that's a positive number. If we were on the other limit switch and the cam were over there, then we would have a negative offset because we're behind machine zero. So that's what the sign is telling us, whether we're in front of or behind the zero position. So the reference offset in this case would be set in the parameters to 28,504, and that would indicate the difference between the cam and zero. All right, now let's talk about how offsets affect positioning. Let's start with the simpler application where machine zero is in the same location as the sensor, in this case in the middle of the travel range. So we set our reference offset to zero. Now, if the reference offset is zero and we have just referenced the drive, the reported position will be zero. It will be saying, I am at zero. And if I issue a go to position zero command, the drive won't move. It will say, I'm not going to move. I'm already sitting at zero. Pretty simple. This is probably the way many applications will work. But let's look at a case where there's a difference. Let's say we define machine zero over here and the cam's in the middle of the travel range. There's no reason it can't be set up this way, and some applications may find it easier to put the cam somewhere else. So what happens here? Well, let's say our reference offset is minus 25,020, and that is because the cam is counterclockwise with respect to zero. That's why it's minus. Now, if we have just referenced the drive and we've just tapped the cam and stopped, you might think, well, shouldn't position be zero? Well, the answer is no, because we're not actually at zero. We're really at the reference offset. So in other words, it's going to report my position as being minus 25,020 when we complete referencing, not zero. That could be a little confusing, but if you stop and think it through, it makes perfect sense. Now, what happens if I issue a go to zero command? It's going to go to the machine zero position. The drive will move because it knows it's not currently at zero, even though it's just been referenced or zeroed. Think about that for a second. All right, so how do we set up referencing? It's pretty simple. There are parameters that you just set in MOVI-C. So what you do is you go to the Functions menu group, you go to Drive Functions, and you find FCB12, which is the function control block that has to do with referencing. You pick that, and you've got a set of parameters that apply to both Drivetrain 1 and Drivetrain 2. Of course, we're only using Drivetrain 1 in our activities, so here are some of the things you can set. First of all, you set the referencing mode or type right here. There's a pull-down list, and you'll find everything I've just talked about. You will find the offset right here. By default, it's usually 0, but you can set it to whatever you like. You can also send the offset over the field bus if you're doing field bus communications. That is another option that's available. Here are the two referencing speeds, the search speed and the retraction speed, and you can set them to whatever you like. Of course, the search speed is typically the faster of the two. There are also two ramps, acceleration and deceleration, for referencing. So referencing has its own independent ramps. And that is pretty much it. It is very simple. It can be set up quite easily, just a couple minutes. And that is the end of session 18. So I hope you found that useful and that referencing now makes a lot more sense to you. If it doesn't, I suggest you watch this session again because you really do need to understand referencing to do positioning. And now we're going to be moving to our final session, session 19, which is also our last lab. We're going to be doing a positioning activity using the positioning MOVI kit. So I hope you find that helpful as well, and we'll be doing our course wrap up at the end of that. So the end is in sight. See you then.